So on these, there's a couple ways to proceed. One way is to write it all as a single radical and then try to break it down as best you can. Say, well, I know a perfect square that divides into it. It's 25. And I get 5 times the square root of 2. And so, that'll work. Actually, I guess it's about the only way on this one. Okay, so let's try another one. This one's pretty similar. So, oh yeah, okay, this one does have two methods. So I could, like the last one, write it as a single radical, which works great, pretty much every time, which will be square root of 72. And then I can say, is there a perfect square that divides into that? Yeah, 4 does, but there's a bigger perfect square, 36. Bam. And the square root of 36 is 6. And then, of course, you can say, plug that in, they give you the same answer. Now, an alternative method on this one is to say, well, I could write square root of 12 as 4 times 3 because I know the square root of 4. And then the square root of 4 is 2. And then it doesn't look anything like the other one, does it? Okay, and then I can write 3 and 6 inside the same radical. Whoops. And a perfect square divides into 18 is 9. And then the square root of 9 is 3. And I still get 6 root 2, even though it looks totally different. But I didn't break any rules, so it's okay. Let's do more of that. So I can pull perfect squares out right away, if there are any, or I can just merge the 27 and the 48. Now, 27 times 48, that gets kind of big real fast, so I'm going to pull out what I can right away. Perfect square that goes into 27 is 9. Whoops. And then a perfect square that goes into 48 is 16. So the square root of 9 is 3. And the square root of 16 is 4. And I get 3 times 4 times 4 is 48 times the square root of 3 times 3. But the square root of 3 times 3 is just 3. And that would be 144. And you know what, let's check it this time because I'm just feeling wild and crazy. So 27 times 4 square root of 48. Oh, wait a minute. Square root of 27, huh? Yeah, that's kind of a thing, huh? And I get 144. No big deal. I'm going to check them every time on the calculator. At least if I was a student, I would every single time. So now we'll do it again, except this time we get to play with variables, and hey, what more could a guy ask for, right? Okay, so I've got 10 times 5 is 50. Cool. And then I'm going to have x to the 4th times x to the 9th. They're all going to end up inside a single radical, so I'm just combining them now. That'll be x to the 13th, and then v to the 9th. Okay, it's a square root, so we're looking for pairs of things that match. Well, I can write 50 as 25 times 2, so that's cool because I know the square root of 25. And then I could say x to the 13th, well, that's x to the 6th squared. That's 12 x's and one more. And then v to the 9th, that's v to the 4th squared. And one more makes 9 of them. So square root of 25 is 5. This guy becomes x to the 6th. This guy becomes v to the 4th. And ones. So then we were just left with the square root of 2. And this x, oh, I'm just underlining that x and that v. And the problem is done. So that's how it goes. Now we do the same thing again, except this time, it's not square root, it's fourth root. But again, I mean, it's not really that big of a deal. I mean, as far as differences. So they're both fourth roots, so I can combine them all. And 10 times 8 is 80. And v to the 6th times v to the 5th would be v to the 11th. Looking for groups of 4. I know that if you factor 80, it's 16, 2 to the 4th, times 5. And then there's a couple of groups of v's with 3 left over. Okay, so there's a group of 2's. And we got 2 groups of v's. And inside that fourth root, we're left with a 5 and 3 v's. And you can go y1, y2, see if they match on the table. You know what? I guess, yeah, I might as well. Let's do it. Fourth root of 10v to the 6th. Okay. So 4 math 5. Fourth root of 10x to the 6th. We don't really need the times sign, but I'll do it anyway. And then 4 math 5. Let's see what else we got here. 8x to the 5th. Okay, so that's the original problem. And supposedly, 2v squared times 4 math 5, 5 v to the 3rd. Okay, so they're supposed to match. Okay, because remember there were equal signs in between everything. So if I go to the table, do they match? Holy cow, I actually got it right. Mark your calendars. This might not come back. So that's all you got to do for that. Okay, now on this one, it's similar to things you've seen in the past, like x plus 2 times x plus 3. And we said, oh, we got to multiply it out. So you would, you have 2 boys, 2 girls. Every boy dances with every girl. Some people call it FOIL. So you'd have x times x times 3, 2 times x, 2 times 3, and you do all the multiplications and everything is wonderful and good. Okay, but what if, well, so we've basically got the same thing. We've got 2 boys, 2 girls. Every boy dances with every girl. So we're going to go multiply those together. So 2 root 7 times, whoops, I'm doing it wrong, times 8 root 6. And then first boy dances with the second girl. So plus 2 root 7 times 5 root 7. And then, okay, so the first boy, he's done dancing with both girls. So the second boy dances with the first girl, minus 7 root 6 times 8 root 6. You'll notice that the 8 there and the 5 there and the 8 there, I'm careful to make sure they're not written under the square root signs. Is that, well, that would not be accurate. Oh, what in the world? Trouble with that. Okay, there we go. All right, so the second boy dances with the second girl, and we get minus 7 root 6 times 5 root 7. Okay, now it's time to tidy stuff up. So right there, we've got 2 times 8 is 16. And then root 7 times root 6 is root 42. All right, now we tackle this guy. 2 times 5 is 10, and root 7 times root 7 is just 7. Now this guy. Minus 7 times 8 is negative 56. And then root 6 times root 6 is 6. Last one. Negative 7 times 5 is minus 35. And root 6 times root 7 is root 42. Okay. So let's combine like terms and do what we can. Okay. I've got 16 square roots of 42, and I'm going to take away from that 35 square roots of 42. So that would give us, what is that, like negative 19 or something? Square roots of 42. Yeah. Okay, so I got that. And then this is obviously just 70. And this is, let's see, what was that, 336? I'm going to pause, double check that. I'm amazing. It is 336. Okay, and I mean, there's no perfect squares that come out of the 42. So there's nothing I can do with that. So it's still just negative 19 root 42. No big deal. And then 70 minus 36 is going to be negative 266. And so that is our final answer. And as always, plug that in on the main screen, plug in your answer, see if you get the same. See if you get the same decimal approximation. If you do, you're in good shape. And if not, go back and find the mistake, because it's always fun to do extra math. Okay, so like we said before, if you're adding or subtracting radicals, everything inside the radicals have to match in order to have like terms. And also, the variables on the outside of the radicals have to match as well. But when you're multiplying and dividing, you don't have to worry about all that. However, the only thing you have to worry about is the indices of the radicals. We've got a 3 and a 2. Remember, square root is just second index. So they're not the same thing. So I can't just say, well, let's just make it all one radical and everything will be groovy and good, you know. So instead, we need to do something just a little different. We need to convert to exponent form. So that'll be 32 x to the 7th, y to the 4th, to the 1/3 power. Convert that third root to 1/3 power. And then 2xy to the 1/2 power. Again, square root is the second root. Now I've got powers raised to powers, so let's see what we can do with this. So we've got 32 to the 1/3, whatever that is, and then x to the 7/3, because when you have a power to a power, you multiply the powers. Y to the 4/3. Whoops, that's not 3. There we go. In the denominator, 2 to the 1/2, x to the 1/2, y to the 1/2. Okay, now, because I don't have, this problem is taking up a lot of space, I'm just going to rewrite that step just a teeny bit. Dang, why is it doing that? That's dumb. I'm going to say, you know what, 32 is actually 2 to the 5th. And we've seen that before. 2 multiplied by itself 5 times. All righty. Now, once again, I've got a power to a power, so 5 times 1/3 is going to be, well, I don't know. Let's see, 5 times. It'd be 5/3. Yeah, of course. Righty. That's a 3. I know it's hard to tell. So look at this. I've got that stuff there. So they have the same base, 2. So I can subtract the exponents. Same thing with the x's, same thing with the y's. So I'll get 2 to the 5/3 minus 7/3 times x to the 7/3. Whoops, I want to write that like this. Minus the bottom exponent, 1/2. Oh, wait a minute. It's not a 7/3 there. Duh. It's 5/3 minus 1/2. I did that. That was goofy. Okay, then for the y's, 4/3 minus 1/2. Okay. Can't combine them until I have common denominators. So, the common denominator for all of them is going to be 6. So I'll multiply by 2/2, 3/3, 2/2, 3/3, 2/2, and 3/3. Bingo. So that's going to be 2 to the 10/3 minus 10/6 minus 3/6 times x to the 14/6 minus 3/6 times y to the 8/6 minus 3/6. Okay, so we tidied that up a little bit. 10/6 minus 3/6 is 7/6. I know, it's like, is this problem ever going to end? Nope. Okay, and then 14/6 minus 3/6 is 11/6. And then 8/6 minus 3/6 is 5/6. And now it's time to do some erasing, because I mean I'm just about done, but kind of out of room here. All right, let's change the color up a little. Okay, so you'll notice, well, first of all, it says write it in simplified radical form. I don't even have a radical. All I have are exponents. So we got to get back to radical form eventually. And now that we're at this point, we can do that. And notice that all the exponents have the same denominator, 6. So I could pull that out of all of them so it looks like this. Because after all, if I say, oh, power to a power, power to a power, power to a power, I would multiply them all out and then I would get right back to here. And so, yeah, it's okay. It works. But the 1/6 power, that's the same thing as the 6th root. Let's see. And now I'm going to shift into eraser mode again. There's a lot on there. Okay. Yeah, let's get rid of all of them. Okay. We would be done, except there's stuff we can pull out because we're looking for groups of size 6. Well, I've got at least 6 2s. Like there's one group of 2s with 1 2 left over. I've got one group of x's with 5 of them left over. And I don't have a full group of y's, so I'll just leave those there. So I will write that a little closer so it doesn't look so silly. And then that is the answer. Now it's written in radical form with everything pulled out. So they're not the toughest problems, but they're certainly not the easiest. So it takes practice, it takes effort. So put it in.